We wish to describe a system of non-relativistic interacting bosons. So we started with the Lagrangian for a non-Hermitian scalar field with an interaction term, a phi-4 interaction term, which corresponds to a contact interaction. That means that the field mediating the interaction has been integrated out. Then we took the non-relativistic limit and we got a Schrödinger-like Lagrangian with, again, a contact interaction. We then went through the process of canonical quantization and wrote our field operator using a mode expansion in a box of volume V. Then we invoked Noether's theorem for the invariance under time translation symmetry of the Lagrangian, and which gives us the Hamiltonian, which is a generator for this translation in time. The expression we obtain for the Hamiltonian is in the momentum basis, in which the kinetic energy term is diagonal because we have a dagger p, AP. And for the interaction in this basis, we see that we have no dependence in the exchange momentum k, so the constant here doesn't depend on k. And that's because we have a contact interaction. So in the coordinate basis, it's a delta function of space, and because all the fields are expressed at the same space-time coordinates. So this specific form of the interaction is due to our specific form of the interacting term in the Lagrangian. And this specific form of the one-body part is due to the fact that we don't have any external potential. So let's write a more general form to the Hamiltonian for bosons. So we have a one-body part which contains the kinetic energy and eventually a trap, an external potential. And we have a two-body interaction. The one-body part is usually easy to diagonalize, so we can easily find the eigenvalues E0I and the corresponding eigenstates annihilated and created by A and A dagger. In the general case, however, the interaction part is not diagonal in this basis, and that's why we have to carry 4 indices, one for each annihilator and creator. The interaction part is usually too complicated for the Hamiltonian to be diagonalized exactly, and therefore we need approximations such as based on the many-body perturbation theory. This approach involves propagators and Feynman diagrams and is heavily based on quantum field theory. And in particular, there is a lot of information we can extract from the propagator of one particle. Indeed, the propagator tells us how a particle evolved from one point of space-time x to another one y, but taking into account all the possible interaction between x and y due to the presence of the other particles which constitute the system. If we represent the many-body state of the system by a state vector psi, we could create a particle on top of this state using the Hermitian conjugate of the field operator phi. So we can create a particle at the space-time position x. We can then let it evolve and later on annihilate it at the space-time position y. And if everything goes as planned, we return to the initial state psi. That gives us an amplitude of probability for a particle created in x to be propagated from x to y and later on being annihilated in y. And that's nothing else but the propagator between x and y for the particle. This expression is read from the right to the left. Therefore, we need to make sure that x occurs before y, and to do that we use a time ordering operator. It's not strictly speaking an operator in the sense that it doesn't belong to the Hilbert space. So its action is to put the later function of time to the left and the earlier one to the right. This way we make sure that we create before we annihilate. But interestingly, if y is before x, then that will reverse this order, and we see that we will have an action of phi first and phi dagger later. So we will first annihilate and then we will create. We can rewrite the propagator using the step function in time, and that way we ensure that when ty is greater than tx, we have the creation in x and later on an annihilation in y. However, if tx is greater than ty, we have first an annihilation in y and then a creation in x. This object, the propagator for one particle, when interaction occurs, it contains a lot of information. For instance, we can extract from it the density of particles in the system. This is the number of particles per unit of volume at a given position x and a given time t. Indeed, we can obtain this quantity by interrogating the Mani-Body state psi with the operator phi dagger x phi of x, which count the number of particles in space-time position x. Indeed, we first annihilate a particle in x if it is there, and there we recreate it. So if a particle is in x, that will return 1. In general, applying that to a Mani-Body state will return the amplitude of probability for the particle to be in x. And therefore, the expectation value of this operator gives us the particle density rho of x. And we see that we can relate that to the propagator by requiring x and y to be equal. But there is an ambiguity because with the same time t, we don't know if we use phi dagger or phi dagger phi. Therefore, to get the density, we see that we need to have phi dagger phi. So we need this time to be a bit later than this one.